So I am good to start, am I?
Yes, I think you should. Hoping the others. I can see Lubna is active. Mohammed, Tamimi, I can't get any indication from them. Yes, but I think you can start.
Brilliant. Okay, well, hello everyone. How are you? Good morning. It's sorry to have pushed the meeting earlier a bit, but I really wanted to thank very much everyone for inviting me to come and give this talk, and I hope it's going to be an interesting one for you. It's not quite the title that Henry has put on the list, but actually it's exactly the same content, which is really looking at early warning systems and how we can think about volcanic risk and whether hazards early warning systems are any good for volcanoes, and there's particular reasons why that might be interesting. So today my talk's called Shake, Rattle and Roll, Communicating Lethal Risks. So how can we actually communicate these types of risks? So some of you may well know that the Boxing Day tsunami in the 2004 in Indonesia was actually one of the sort of very big events that really woke the entire world, and particularly the United Nations, up to the importance of early warning systems and the need to discuss about how early warning systems work and how we communicate these kinds of lethal risks, and also how we can do all sorts of different types of disaster risk reduction better. And what was really interesting about this event, aside from the fact that, you know, over 250,000 people died from this event, was largely just the sheer scale of the event. So here I'm just showing you a simulation of what the tsunami looked like as it was generated in Aceh in Sumatra in Indonesia. And you can see that clearly there is populations that were living very near to the earthquake. The earthquake would have destroyed a lot of the buildings surrounding the area, and shortly afterwards the tsunami would have been generated and hit those people. And that's where a significant amount of the deaths happened. But of course, there were deaths that happened all across the Indian Ocean, right through to Thailand as well, who were sort of 2 or 3 hours away. And one has to think, you know, why is it that so many people died when actually there was sometimes 2, 3, 4, 5, sometimes 6 hours notice where that warning could have even been passed on. So there's sort of a lot of questions here about, you know, how we can communicate to those that are near field to an event and those that are far field to an event. So if we look at the chronology of the event, you can see here on the left, the chronology is showing you just how quickly the tsunami hit the Andaman and Nicobar Islands. But then, you know, just within an hour or two, how it was hitting areas such as Thailand and Sri Lanka, who had quite extraordinary death tolls as well. So what was so startling about this event was the main reason was that there was no early warning system in place for the tsunami. So unlike the Pacific tsunami warning system, which has been set up for now over 70 years, there was no such system for the Indian Ocean. And so even though many organizations and institutions picked up the earthquake and thought there could be a tsunami, they weren't actually able to communicate that. What was interesting is that nearly all of the victims were taken by surprise. And what's interesting about this is that, you know, it was largely because it was Christmas time. There were a lot of tourists from around the world enjoying the warmer weather, particularly those from the Northern Hemisphere. But also a lot of the people that worked in those resorts were people who lived in who'd come from different countries or come from inland and didn't really have any understanding or oral tradition or history of tsunamis. Now, tsunami detection itself is quite a difficult thing to do. It requires a lot of sophisticated technology and it's pretty expensive. And that's one of the reasons why an early warning system wasn't set up in the first place. And of course, there's no point in having an early warning if you then can't communicate that to everyone. So actually, there needs to be a communication infrastructure that's set up that can communicate across many different countries. And of course, like many countries in the world, many countries in the region of the Indian Ocean, and indeed across the Pacific Ocean, do not see eye to eye politically. And there's all sorts of challenges in terms of trying to communicate across those political and economic boundaries that make things difficult. So we can see that when we're looking at communicating lethal risks, this is actually incredibly complicated. Early warning systems are one of the very useful tools that can be used to try and shape and guide that communication process. Early warning systems are very difficult to define. There's lots of different definitions. As you may know, if we look at any disaster risk reduction term, vulnerability, risk, exposure, resilience, many different types of definition. But really what's very useful is to look at the definition by the United Nations in 2003 that says there's the provision of timely and effective information through identifying institutions that allow individuals exposed to a hazard to take action to avoid or reduce their risk and prepare for effective response. So it's really about making sure that that information is effective and timely. And timely is one of the things that we're going to run into as a big problem for volcanoes. So an early warning system will require a number of different indicators. So if we're looking at a tsunami, for example, we would look at measuring seismic waves, detecting the earthquake, and then trying to see if that generated a tsunami by using buoys that sit out at the sea. That will need to be monitored, and then once something's been detected and verified, a warning will need to be issued. And usually this is the point where a lot of people stop and think that the early warning system is complete. But of course it's only the first 3 stages of many, and actually what needs to be made sure, what is happening is that the warning is being communicated, that people are actually receiving the warnings. There's no point in just communicating it out there if people aren't actually getting it. Also, they need to believe in it, so that means trusting the authority or the institution that's providing that warning, and then of course acting on that warning. And that means actually knowing what to do. And unfortunately, you don't magically know what to do in a situation on the spot, despite the fact that you might be given some urgent information. That's where the preparedness comes in terms of being able to make sure that people are aware of what they need to do prior to an event happening. So that's really the preparedness element of it. Now, of course, this is very difficult to implement, and we can see in the Indian Ocean example, we can see that there's lots of complexities involved in spatially the vast amount of countries that were affected, in terms of the timings, like how much notice can we actually give people. Those that lived in Banda Aceh had very little time compared to those in Thailand. Also, in terms of function, what is the early warning system for? Is it to protect people? Is it to protect infrastructure? Is it to protect businesses? So there's all sorts of different types of early warning systems that might have specific focuses. And of course, finally, one of the main issues that we're seeing today, that was something that came up quite a lot in a recent conference I went to in Italy called Cities and Volcanoes, is the need to deal with multiple hazards. Of course, when we look at many individual hazards like earthquakes are a primary hazard, generates a secondary hazard of a tsunami. But of course, we often get tsunamis and cyclones happening at the same time with the earthquakes. How do we actually deal with that? Can we have one early warning system that caters for all? So the United Nations has developed what is called this people-centered model, which is this idea that there's these 4 different blocks of things: risk knowledge, monitoring and warning services, dissemination and communication, and response capacity. And pretty much based on what I've just told you is the essence of how they came up with this block. And they were saying that these 4 things are really important, and therefore we need to understand how they work, get better science, have better engagement and better communication in order to make these things work. But what I want to do in this talk today is actually use volcanoes to exemplify to you that actually this model isn't actually that useful. I want to use volcanoes to look at how early warning systems have failed or have not done so well, and the different dynamics, because actually what this block tells us is the things that we should have. We can say, yes, we've got our monitoring system, yes, we've educated everyone as to what they need to do, yes, we've got our communication system, but actually how do these things link together? What is the relationship between them? And that's really the important part, where we can learn some really important lessons about how we can improve communication, particularly of lethal risks. So how do scientists make sense of hazard data? Well, I'm going to be using volcanoes as my main examples throughout this whole talk, because I'm a little bit of an enthusiast for volcanoes. If any of you have met me, you will know that. So for those of you who are not familiar with volcanoes, just give a little bit of an overview. Volcanoes are probably the most complex natural phenomenon on the face of the planet, if not in our solar system, in the sense that volcanoes produce a huge amount of different hazards that occur across a wide range of spatialities and temporalities. So what I mean is that we can have lava flows like we're seeing in Hawaii that occur very close to the center of the volcano, the vent of the volcano. But equally, we can have an ash cloud that forms that can affect people 2, 3, 4, 5,000 kilometers away. And so we're looking at very different distances. And of course, ash falling from the sky has a very different type of impact on people than, say, a lava flow. So we've got lots of different hazards that exist that you can see in the diagram. And, you know, these can lead to other types of hazards, such as tsunamis, earthquakes, floods, shock waves, and lots of noxious gases. So those are kind of the primary hazards. Then we get the secondary hazards, which is basically volcanoes do a lot of destruction to crops. This can affect livestock as well, animals that are grazing on the contaminated and polluted agricultural land. You get water contamination. This, of course, all of these things lead to all sorts of health problems, often leads to famine because crops fail or animals die, and a huge social economic disruption. And if the volcano is big enough, it will also have an extremely large impact on the climate and global temperatures as well. So these are pretty extreme hazards that range from being pretty mild to pretty much catastrophic, and causing mass extinction events. So, you know, they really sort of have a good range of activity. So the research that I want to use to explain to you this first point of how do scientists make sense of data was done during my PhD studies, where I studied at the United States Geological Survey. These guys are one of the most sophisticated geological surveys in the world that monitor over 108 volcanoes in the United States across different regions. You can see Alaska, Hawaii, Yellowstone, that I'm sure you've heard of, but of course the Cascade volcanoes, including Mount St. Helens and Long Valley as well. And so what they did was, as various volcanoes erupted on the mainland and in Hawaii, they developed a warning system, essentially, to look at how a volcano is behaving, and is it ramping up to volcanic eruption, and how can they communicate that. And they came up with a warning system called a volcano alert level system. And this alert level system, as you can see here, is a very basic kind of system, which pretty much says, you know, happy volcano green. We've got, you know, orange is starting to get very angry, and red is angry and putting the ash up. So, you know, it's a very simplistic model, but it really does convey the point pretty well. And the idea is that you create these boundaries in order to decide what's happening with the volcano. Now, when I started the research, what happened is they just implemented the alert level that you can see in front of you now, which is a standardized alert level system. Before, they had all these individual ones that were designed locally, and then they sort of developed this standardized volcano alert level system, which, as you can see, is a little less easy on the eye than the color system using words. So what's interesting about the warning system for volcanoes is that volcanoes often do not give much notice as to when they erupt, and when they erupt, there's not enough time to evacuate people or respond to it. And one of the reasons for this are this phenomenon that you can see in front of you. I'm hoping that none of you have ever seen this kind of image before. This is a pyroclastic flow. This is actually from Mount Pinatubo in 1991. And this is the most deadliest force on the face of the planet. This is basically hot gas and ash, shards of rock and glass, traveling at around 450 miles an hour, so that's about the speed of a jet plane, down the side of the volcano, and it will pretty much destroy everything in its way. Now, thankfully, that car, the little van you can see, survived because it was moving at 90 degrees to the actual flow itself. But it raises a huge problem for volcanologists, because when a volcano erupts, it can generate these pyroclastic flows, and it only gives a few minutes in order to evacuate people if they are in harm's way. Now, obviously, that's not acceptable. So if we're taking true good disaster risk reduction to heart, we should be evacuating people beforehand so that they are safe. Now, of course, that means we have a bit of uncertainty because we're not quite sure when the volcano is going to erupt. So it means that we have to take a precautionary approach, and that's really difficult. We're basically starting to look into a crystal ball and try and say, we think this volcano is going to erupt, therefore you guys need to evacuate, and hope that if the volcano is going to erupt, it does it before people get pretty impatient and want to go home and resume normal business. This is, of course, one of the key problems that we see when we're trying to implement disaster risk reduction. You've probably seen this table many times, but I particularly like this table because I know that many disaster scholars like to define disaster risk in all sorts of different ways, with all sorts of different equations. But actually, I think the key thing to think about here is that risk is made of the vulnerability, the hazard, the exposure, and the resilience. It's all of these things coming together that create that risk. That's how the disaster world looks at risk. Sometimes scientists, particularly volcanologists, have a different idea. So in the scientist world, a hazard, they tend to focus on just the phenomenon itself. And they see risk, which you can see in the picture of Naples with Vesuvius there, as something that actually is something not to do with the scientists. How the volcano impacts society is not really the responsibility of the scientists. That's up to government officials, civil protection, emergency managers, and so on. So they tend to sort of view this as a separate thing. And this can make things pretty complicated and difficult when we're trying to work across this difficult precautionary boundary. So as part of my research, I went and spoke to all sorts of scientists, civil protection and emergency managers, media folk, all sorts of different government agencies, to talk about their alert level system that they use in the United States and try and understand what are the challenges and the problems of using such an early warning system for such a complicated phenomenon such as volcanoes. And so I have, sort of two key findings, and I come back to a third in the next section. But one is really about the challenges of scientific uncertainty. And this goes for many, many different hazards, but particularly with volcanoes, there's a lot of uncertainty in terms of constructing what is going on now. So actually being able to know, what is the volcano doing now? What is it likely to do? This is because volcanoes have such a wide variety of volcanic eruption styles, hazards, durations. They can also change behavior. You know, Hawaii can easily go from being a very gentle, effusive volcano to actually being a lot more explosive. And so it can change its character a lot. We also need to make sure that, you know, if we're going to have scientific data, that we're actually getting that through monitoring capacity and resources. It might terrify you to know that only 10% of the world's volcanoes are actually monitored. So if we're not investing in monitoring on these sites, we don't actually know what's going on. We also then need to interpret that monitoring data, which is regarded a bit of an art form. If you were to give 10 different seismologists the same data, I can bet you'll get 10 different opinions about what they think might happen. And this makes it difficult because they need to come to some form of agreement in order to pass that information on to civil protection. And one of the other really big challenges that the United States Geological Survey scientists in particular found very difficult was trying to box volcanic activity into those 4 different alert levels. Is it normal? Are we at a watch? Are we at a warning? How can we actually tell that we're at that point? And it's very, very difficult. It's a huge continuum. One of the main challenges that we saw is that basically volcanoes have different personalities, which is, I'm going to read you a really great quote to exemplify this. And this is, and then this image of this very famous old traditional game operation will make sense to you. So a quote that I got from one of the scientists was, oh, I've just lost it, 1 second. Oh, I've just lost it. Hang on 1 second. I have it on a piece of paper here, but I have just lost it. Where have you gone? Bear with me 1 minute. I pressed the wrong button. Right, here we go. When I try and describe this problem to people, I often use a medical analogy. You know, there are a tremendous amount of people there is a tremendous amount of information about the population of people, about the percentage of people who will have a heart attack. But when you come down to one person, you can't say, well, you are going to have a heart attack at the age of 63. We can say that 35% of the population will have a heart attack by 63, but we can't say anything about an individual. And that's really the point here, is that the volcanoes, each volcano's got that individual behavior, like each of us in terms of our persona, our personality. And it's very difficult to apply our understanding of previous behavior of that volcano and also from other volcanoes around the world to that in order to make assumptions about what we think the future behavior is going to be. It's really, really challenging. One of the other challenging things is being able to accommodate the contingencies involved, and that includes the unique individual behavior of a volcano. The alert level system really only talks about eruptive behavior. It doesn't talk about all sorts of other hazards that might happen. So for example, you can see here a warning system that's been developed in Hawaii to look at sulfur dioxide. Whether Kilauea is erupting dramatically, as we've seen recently, or less dramatically, and it's going through a more quiet phase, there's still sulfur dioxide that's coming out that is affecting people, especially those that have asthma, and that causes a lot of discomfort to people. And so but that's not included in the alert level, because the alert level is only looking at the eruptive behavior. We also have to think about the fact that there's lots of different institutions that are involved. In this case, the Department of Health, that have to work with the scientists on the observatory, and also the national park in which the volcano is part of. And those all have various responsibilities and legal remits that they have to fulfill as well. So this makes it very difficult to accommodate all of the complexities within just this one alert level. My main second finding, which is actually really quite controversial, is that actually scientists do tend to negotiate social and environmental risks when they are trying to decide what alert level they're going to assign. So, for example, somewhere like Hawaii, people are experiencing volcanic eruptions all the time. And so actually they're pretty used to getting quick information, they know where to get it from, and to respond quickly and to know what to do. But in a country, say, where a volcano hasn't erupted for a long time, like Mount St. Helens in the United States in 1980, it's actually, you know, people didn't really understand the potential scale of the event, what the implications were, and the damage that can be done. And so actually scientists do tend to consider actually the risks involved. And although many times they're only legally required to focus on the phenomenon and talk about the science, they do actually think about how are people going to respond. If this is a community that's not used to volcanic behavior, perhaps more time needs to be spent building up educational capacity so that people can actually then be able to respond when the risks get higher and the hazard is displaying heightened signs of unrest, than say somewhere that is very familiar with things and can respond very quickly. And this is quite controversial because a lot of scientists don't like to admit that they're doing the job of the emergency manager or civil protection, but actually in reality, in many cases, that is what's happening. And it is about bringing together the different expertise from the scientists and the civil protection to try and find the best way forward, because no one person has all the answers. So it's a very complex thing that the USGS has to do, but they do a pretty good job of it. And as you can see here, that you know, the scientific uncertainties are high, make it very challenging, and also that they are taking into consider the risks because there's such great uncertainty. So, okay, we've looked a little bit at how we can look at data, hazard data, how we can make sense of that hazard data. What I want to do now is talk a little bit about how scientists share that hazard and risk information. So what do they actually communicate? And there's a really good lesson to be learned from this example here from Nevada de Ruiz in Colombia. So this is a volcano that in 1984 started to show some signs of unrest. So scientists came in and started to look at the volcano. They were obviously very concerned that this volcano had an ice cap, which you can see in the image there, because what that means is that when the volcano erupts, it will melt the ice and create what is called a mud flow or a lahar. So what they did was they generated a hazard map, which you can see in this picture here. So we've got Nevada de Ruiz in the center of the yellow circle on the left, which shows where all sorts of pyroclastic flows have happened as well. But if you follow the river channels, you can see that there are mud flows that have happened in the past. So these grey areas, and they've happened several times in history. So we kind of know that there's going to be a lahar the next time the volcano erupts. So this map was developed by the scientists and was given to the government, and the local government felt that this was too alarmist and asked for the map to be revised for November the 12th. This is basically a classic example of people trying to ignore the fact that they are at risk and therefore need to do something about it. And unfortunately, what happened was the very next day the volcano erupted. This is a picture you can see of what used to be the city of Armero, which is still there today. It's been somewhat rebuilt. 23,000 people died during this event. The lahar traveled 70 kilometers down the valley, and as soon as it hit that flat ground, it spread out, pretty much destroying everything in its sight. One of the reasons the local authorities didn't respond to the fact that scientists had actually told them the volcano had erupted was partly because it was a period of great festivities. There was lots of football matches and fetes and festivities going on, and they didn't want to disrupt that. And unfortunately, they ended up with a disruption that was far, far more significant than what they would have had to have done. So really, the point of this real tragedy, because really 23,000 people died from a very, very small volcanic eruption is an absolute tragedy, was really, as Barry Voigt has stated, and Barry Voigt, for those of you that might be interested in a little bit of volcano celebrity, is the uncle of Angelina Jolie. But he said, basically this event was caused purely and simply by cumulative human error, by misjudgment, indecision, and bureaucratic short-sightedness. So really, that is what caused this problem. It wasn't the scientists who weren't able to share the scientific information or share the hazard information, or even say, look, the volcano's erupted, there's a lahar that's coming your way. If the people who have to make the decisions to evacuate and pass that on to the local communities have not acted before that point, even at a last case, worst case scenario at that point, then this is the kind of things that happen. So the United States is actually a really good example of how we can engage with different stakeholders. And here you can see that they have all sorts of different ways of engaging with federal departments and the public to try and manage these types of crisis. And there's all sorts of different tools, communication tools, that are set in place as part of that early warning system. So you can see the sort of unidirectional communication on the left-hand side of the slide is basically the observatories just issuing information, and that's basically what our alert levels are, or what hazard maps are, or what briefings are. You know, they're very sort of, this is the science, we're going to write it up in a report and you can respond to it. But there's also a lot of multi-directional communication. That's between the observatories, the whole USGS program, and different agencies and departments of the government that work together to have staff meetings, that have internet websites and share information, and contact each other individually, so that, you know, when a crisis happens, you can pick up the phone and say, hey Bob, it's Joe here, this is the situation, and Bob and Joe know each other, and they're able to kind of trust one another and have a relationship and know what they need to do. And that's really important when we're looking at trying to engage stakeholders. Finally, the most sort of important part is the preparedness part. This is establishing communication plans. So this is making sure that everybody knows what they're doing prior to an event, that everyone's fulfilling their institutional protocols and procedures, and of course fulfilling any kind of policy, law, or legal requirements of that country. So it's really important that in order to share hazard and risk information, that all stakeholders are being engaged in multiple communication ways that are facilitating all different types of communication and engagement. It's also a little bit about the timing. So scientists are, what I found in my research certainly, was that scientists are quite reluctant to give a warning until there's actually quite a high certainty that something is happening. But actually, many times the user groups, so the emergency managers and civil protections, want less certainty, but more information more rapidly, so that they can make decisions about how much risk they're willing to take on. And so that was one of the main frustrations that I found, was, you know, that the forest management around Mount St Helens, for example, were very frustrated that scientists were taking so long trying to decide the exact wording of things, when actually what he wanted them to do was just to pick up the phone and say that this is the latest information, this is what we think's happening, but we're not sure. So, you know, it's that idea of not being precise. Also, there's the need to, during times of quiet, or peacetime as we call it, to make sure that that there's all sorts of plans and protocols being put into place. Finally, when we're thinking about communicating, we also want to think about generating meaning in alert level messages, or any kind of communication. What I'm saying to you and how you understand what I am saying could actually be very different. It's basically an idea of coding and then decoding this kind of information. We know that cultural, political, economic, linguistic factors play into how different people can hear the same words being spoken, but actually interpret them in a very different way and then act differently according to that. So it's really about making sure that there's complete clarity in communicating a message. A good example is when we look at the percentage of rain. As you know, here in the UK, we get lots of rain and we love to talk about it all of the time. So one of our favourite things is to open our weather app every morning and look at what the percentage of rain is. But what does that actually mean? What does that percentage of 30% of rain actually mean? You know, in Gerd Gergenser, he's written a wonderful book called Risk Savvy, which I definitely recommend you read. Gives us a really good example here how some people think that if it's 30% chance of rain, it means that 30% of the day it's going to rain. It's fair enough. Other people think that only 30% of the area of land that's part of that forecast will rain. And others think that actually 30% of meteorologists think it's going to rain that day versus the other 70% who don't. So which is it? Which is it? I mean, we all hear this number. What does it actually mean? Would you put an umbrella into your bag if it was 30% chance of rain? Well, what it actually means is that based on exactly the same conditions that have been seen on other days, on 30% of those times, there's actually been rain. So we can say that based on the conditions of today, from the past, we can say there's a 30% chance of rain. And of course, that's not something that's very easily broadcast on the news and the weather. So people don't necessarily know that. And they're not necessarily being silly for thinking it's potentially any of the other three options that I've given here. So we have to make sure that we're really clear about what we mean by percentages or what we mean by levels of danger or risk. Equally, we have to think a little bit about what risk really is, because scientists tend to present risk as a probability, as a known loss or gain. And there was this wonderful book by Frank Knight who really said that we really need to start distinguishing between risk and uncertainty. And I know you're looking at this, Carina, and thinking, Carina, this is a quote from 1921. And I think actually almost 100 years later, we are still having this problem, because what Frank Knight says is that unless we can measure an uncertainty or risk proper, we should be using the word uncertainty. So unless we can actually roll a die and say we've got a chance of 1 in 6 in getting the number 2, that is a proper risk. If we can't do that, then we have an uncertainty. And so weather, for example, kind of sits a little bit in between, because we have enough statistics about the weather. It happens enough that we can kind of almost call that risk. But of course, with volcanoes, we don't have that type of data, and so that would be seen as uncertainty. And one of the key problems we have is thinking about how we distinguish between risk and uncertainty. And this became particularly prominent during the L'Aquila controversy that happened in Italy during an earthquake that happened in 2009, which killed more than 300 people. I'm sure you may have heard of this event, but one of the key things from this event was that essentially what happened was that the civil protection and scientists involved gave some pretty poor communication about what they expected to happen. There was a lot of seismic activity, and they were concerned that that it would well, the populations were concerned that it would get worse. And the authorities felt that because there was lots of little earthquakes, there couldn't possibly be a big one. Well, they knew that it could possibly be a big one, but they basically communicated, we don't think that a bigger earthquake's likely. We think you should just go home, relax, have a glass of wine, and don't worry about it. Of course, what tragically happened was that a larger earthquake did happen. A number of the buildings collapsed, whereas people might have gone to stay with family or slept in their cars as they traditionally did. during times of unrest, they went home. And so the local population put a case out that went to court, basically saying that, you know, that those people should have given us a different response and should have communicated better about what the risk was. They should have said, we don't know if there's going to be a bigger earthquake or not. There could be, there might not be. So what we want you to do is take relevant precautionary actions that you and your family feel safe with, and these are what those might be. So essentially a whole bunch of them were sentenced to jail, but they never actually went to jail. He's only now the one civil protection member who is still sentenced to jail. They were acquitted. But actually what happened was rather more severe in a way than people going to jail. What it meant was that scientists became incredibly scared to speak out about any types of uncertainty or risk. They were worried that if they gave information that was incorrect or perhaps, you know, had been not clearly communicated or someone had rephrased them, that they would end up in jail. And there's been all sorts of questions about legal protection now, like how could you as a scientist be legally protected? You know, you don't want to end up going to jail for trying to stop people from dying from a pyroclastic flow from a volcano, but equally you can't look in a crystal ball and say when that's going to happen. And the really sad thing about this event is that really it's removed transparency and goodwill and made communities, the scientific community in particular, incredibly scared about communicating uncertainty and risk. And of course, as you remember in my first, the previous section, one of the key things to making a success is actually communicating across that hazard and risk boundary and trying to talk things through, because there is no one key expert. So, you know, this is kind of like a really, really, really big shame, and it is a big problem. So my last section, I kind of quickly want to take you through why it is that, you know, the expert is important, and we think about expertise and accountability, particularly following the L'Aquila crisis. So some of you may remember this volcano, the unpronounceable volcano of Eyjafjallajökull that erupted in Iceland in 2010. It was pretty explosive. It pretty much brought the whole of the European flight paths to a complete standstill. Most countries were completely landlocked. And the reason was because of this volcanic ash. Now, the reason that this event, well, why planes were actually banned from flying in volcanic ash is partly because of this event that happened in 1982, when a British Airways flight flew over Mount Gunung in Indonesia. And what happened was the plane lost all 4 engines, and the captain said, so Eric Moody said, ladies and gentlemen, this is your captain speaking. I'm afraid to tell you we have lost all 4 engines. We are doing our damnedest to get them under control and hope that you are not in too much distress. Well, I know I would be pretty scared, but actually everyone on the plane was pretty calm. The pilot was able to glide the plane 180 degrees because he figured out that he hadn't been in this problem before. So he glided, turned it around 180 degrees, and then the engines were able to start up and he was able to land the plane safely. It was a very close call. And indeed, these are the photos that Eric Moody then took of the engine following the event. And what you can see there is an engine that's got a whole load of glass stuck onto it. And you can see in this image here, what happens is that when we look at a jet engine, it basically sucks in the air and heats it all up and propels it out the back. But when that air has got volcanic ash in it, it creates a problem. Volcanic ash is essentially silica dioxide, which is glass. That glass then gets sucked into the engine, it heats up in that combustion chamber, it melts and it lines the turbine, which then chokes it and causes it to fail, and therefore you can lose the engine. So, you know, unsurprisingly, a group of people got together and said, well, we can't have this doing anymore because A, we don't want planes falling out of the sky. That's not very good for aviation travel. And B, we want to make sure that we reduce the damage to our jet engines. You know, jet engines are very expensive. They're anything between 20 and 80 million pounds each. This is a huge expense for an airline, so you kind of don't want to damage it too much. So they developed this early warning system that brings together the Met Office with volcano observatories, with all sorts of satellite data, with the pilot themselves, who can quite often see when a volcano is erupting before anyone else. And they developed what are called volcanic ash advisory centres. So these are centres that guide aircraft and aviation on where volcanic ash is and how to avoid it. So the problem was that in 2010, we had this procedure put in place, this protocol globally that said, if there's volcanic ash, you shall not fly. Now, unfortunately, when we had this massive ash cloud from Iceland covering pretty much most of Western Europe, what that meant was all of those countries that have an incredibly crowded flight path weren't able to fly. Many of them were landlocked. They couldn't actually travel out of their own country except by road. They couldn't fly in and out because the ash cloud covered the whole country. And of course, many of those countries were wondering why they were being affected by a volcanic activity when they live so far away from volcanoes. The Volcanic Ash Advisory was issued by the Volcanic Ash Advisory Centre, and this basically uses models to try and figure out where they think the ash is, where the wind's blowing it, and at what different heights. And of course, this was then used to determine where planes could or couldn't fly. And this was standard procedure. This is a model. We don't actually know this for real. This is a model that's generated, partly because it's very difficult to measure where ash is in real time. It is possible. There's this technique called LiDAR, light detection and ranging, which is basically radar that sits on the ground and sends a beam upwards, and that can detect any volcanic ash. You can see on the image on the right there, you can see the red volcanic ash cloud that's been detected because it's denser, heavier material. If you had enough of these on the ground, you could monitor volcanic ash in real time, but unfortunately these machines are incredibly expensive and there's not many of them around the world. So we're not at that stage yet. So what was difficult, really, what came to light in 2010 was two key things here. We had lots of uncertainty about where the volcanic ash was, how we can monitor it, and what the concentration of it is. So there was a need for more scientific information and technology to help reduce those types of uncertainties. But equally, there's big questions about the risk. Nobody knew how much ash needs to be thrown at a jet engine for it to fail. And it is unsurprising that actually nobody like Rolls-Royce really wanted to do experiments with their 50 million pound engines, chucking ash at it to see at what point does an engine fail. It's a very, very expensive thing to do. So what was really interesting was that after 5 days of UK airspace closure, which was unprecedented since the Second World War, the Civil Aviation Authority in the UK and across Europe decided to put in new regulations. And they determined a safe ash limit of 2 micrograms per metre cubed of ash. They then removed the flying buffer zone of 60 nautical miles. And then even later, they felt even more comfortable that actually they're going to introduce a time-limited zone where aircraft can even fly through this ash for a limited time. Well, this is interesting, isn't it? Because basically, for the last 30 years, we've been in the dark about what a safe ash limit is. And suddenly there's these limits that have been put in place. Where have these come from? Who decided them? Well, it seems that people, particularly engineers, were pretty much locked up in a room and told to come up with a value. And why were they coming up with a value? Because of social and economic pressure. The UK government, European governments were under huge pressure, economically by the aviation sector, economically by businesses, all sorts of disruption was happening. There was travel chaos, people were stranded. You know, blood supplies weren't even being sent to Australia, where they had to cancel operations because they couldn't get the same blood types and matches that they needed from Western Europe. It was just extraordinary, the types of pressures that was being placed on not being able to fly, and really shows how interconnected and global our world really is. So that was really driving the changes, but really there was a lack of scientific evidence of which these policies and procedures were placed, and it really was about lobbying. So whose risk counts? At this point, was there consideration for the population who were on the plane, thinking about what's the safest thing for them, or even the cheapest thing for aviation? Or was it about all these other people who were suffering economically and sometimes health-wise as well? So when we look at a crisis like this, we can see that when we're communicating lethal risks, there's all sorts of different things that we need to take into consideration. This makes it incredibly difficult. So to sum up, we need to be a little bit more risk savvy when we're thinking about communicating lethal risk. And you may remember I was talking about that model by the United Nations in terms of early warning systems. And I think what I've tried to show you a little bit here is that actually the problem isn't in the risk knowledge or the monitoring and the warning and the dissemination and communication and the response capacity. Obviously, there's lots of work that can be still done in those boxes, but the reasons that early warning systems and communication fails is actually due to the things that link those different things. So that means having effective and continuous communication networks, making sure that education and availability of scientific knowledge is available, considering multi-hazard situations, integrating scientific research into practice and practice into scientific research, developing good governance and effective decision making, increasing preparedness, awareness and trust. Key here, defining accountability and responsibility as highlighted by L'Aquila, and also increasing the participation, perhaps a major failure of the Nevada de Ruiz eruption. So you can see here that really it's the links that are repeatedly causing a failure of the early warning system. And this is something that you can read more about in the paper listed at the bottom there, that reviews a number of different early warning systems across a number of different hazards to highlight this. So in summary, if we want to be a bit more savvy in terms of our communication of early warning and risk, what we need to do is have effective early warning systems that can communicate uncertainty clearly. There are always going to be inherent uncertainties in scientific understandings, and that needs to be communicated. We also really need to make sure that we take into consideration the local contingency and the cultural, economic, social dynamics, as well as the scientific dynamics, making sure there's clearly defined roles and responsibilities, challenging the benefits of standardized procedures, as we saw with Ayefyekli-Yokla. You know, that standard approach of having ash in the air and not flying was no longer acceptable anymore. Improving education and response, and thinking about who has the power to make decisions. So, I mean, I used to work in the financial sector, and of course we know in finance that there's this saying that cash is king. You know, if you have cash, you can do anything. But I genuinely think that in the disaster world, communication is king. If we're all communicating in an open, honest, and integral way, then we can avoid a lot of the pitfalls and reduce the number of disasters that we see. So this wonderful quote here is one final one to take away. Recognizing the social role of scientific uncertainty will help us to see how many of our problems about risk are deeply cultural and cannot be overcome simply by the application of better and more and better science. So thank you very much, all of you. I hope that that was useful and interesting for you and made sense. Does anyone have any questions for me?
Hi, Carina. I have one.
Okay, hiya.
Regarding tsunamis, as you know, that McFarland Fault, in case an earthquake happening in there, we have exactly nearly 20 to 30 minutes of time span until a tsunami wave hits the coasts of Oman. So putting that in consideration, why would we put an effort to develop an early warning system when one of the main components is that we need to, the main components of the early warning system to succeed is to give enough time for the recipients to react, and in order to reduce risk and exposure. So what would you say about that? You got my question?
Yeah, no, it's a good question. Well, you know, the main, when you've got a community that lives within close proximity or near field to a tsunami, this is a really big problem, and I don't think there's a particular solution at this time. However, one of the major early warning signs is, of course, the earthquake itself. And so if people feel an earthquake, they should generally try and get to an area of safety, irrespective of whether it generates a tsunami or not. Now, there's a slight caveat to that, because some tsunamis can be generated by landslides, and you wouldn't feel
volcanoes also,
and volcanoes, of course. So, but most of the tsunamis that we've experienced lately are seismic. So, and particularly in Oman, we would expect that there would be some earthquake activity, even if that then led to a
but most of them happen in the middle of the sea, so it's difficult for us to feel inland of any shock waves.
Oh, exactly. So one of the things is that if you've got such a short time span in terms of being able to provide a warning, say you have got monitoring equipment that has picked it up, is to make sure that you have invested in infrastructure that means that people can get to safety. So in the case of places like Muscat, which are quite low-lying on the waterfront, that means building vertical evacuation structures so that people can climb to above what the tsunami wave height would be in order to get to safety. Now, this is the ideal solution, or you could have like a submarine that you get into that protects you, so that when the wave comes in, you're protected by this sort of submarine structure that's very robustly built. All sorts of engineering solutions that can be done. The main problem with this is that, you know, people need to know where to go. They need to be physically able to get to those places. People with disabilities, the elderly or children might take longer than the required time or available time to get to those.
Yeah, but no evacuation could happen in less than 30 minutes. That's
exactly.
Impossible.
I mean,
especially if you're requesting them to go to highlands. I mean, the nearest mountain we have here is a couple of kilometers away from us, so it's not easy.
That's
and put in consideration if it happens in the middle of the night, waking up, realizing what's going on would take time. So
exactly.
I know it's a difficult scenario to sort out, but it was just a question that I had to ask. If we needed to convince the higher authorities to invest in early warning system, maybe that's a question we might have.
Yeah, and I think that, you know, early warning systems are useful in near field tsunami instances, but there's no point in having the early warning system if you then do not give people the ability to get to safety, and that means having these evacuation structures. People can't walk to the nearest mountain in time. Not going to happen. So you have to create these safety structures that people can get to and make sure that they're high enough. And, you know, Tohoku in Japan, that tsunami showed there were some failures there, but there were some great successes. And in some places, people were able to get to safety, and they also didn't have a very long time. It is possible. It might be that you're only ever going to be able to save the fittest, sharpest, most awake at times.
Survival of the strongest.
Yeah. So, but, you know, without the early warning system, you have no hope at all. But if you don't have an early warning, if you have an early warning system, there's actually no point if you don't then give people the ability to respond. Right?
Yes.
And get to safety, and that's a challenge. And you know, Lumna, you really hit the nail on the head, because this is, I think, one of the biggest challenges that we have for natural hazards, because with volcanoes we can sort of generally we can see something's bubbling, so we can kind of go, yeah, we think there's something going on, and people can usually see or feel it. But of course with a tsunami it just happens, that's it, you know.
Yeah.
And that makes it incredibly difficult because we can't take a precautionary approach. We have to have a responsive approach, but that means putting a huge amount of investment in preparedness, which quite often just simply can't be justified cost-wise when, you know, hospitals need beds and educational programs need money, and that's the challenge that's faced.
Thank you
Okay.
very much, Carina.
That's all.
Any other question, please? Okay, Mohammed, you want to ask a question?
Yeah.
No, thank you, Mr. Henry.
Okay, in that case, then
No question.
we call the seminar to end. Thank you very much, Carina, for the presentation, and I hope it has been beneficial to everyone. Okay, let's just say thank you to Carina.
Thank you. Thank you all for listening. Thank you.
Okay,
Thank you, Carina. Thank you very much.
Before you leave, I have one announcement to make, please. The seminar next week on Monday might be shifted to maybe Tuesday, because I'm trying to see if the appointment that I've had, which is urgent, I can postpone the date. But I'll put an announcement on Bright Space to that effect maybe tomorrow. So I just want to crave your indulgence that we may move the seminar to the next day.